The SpaER method, introduced in this paper, revolutionizes fetal brain motion tracking by leveraging equivariant filters and self-attention mechanisms to learn spatio-temporal representations. Unlike conventional approaches that statically estimate fetal brain motions from pairs of images, SpaER dynamically tracks the rigid movement patterns of the fetal head across temporal and spatial dimensions. This is achieved through an equivariant neural network that efficiently learns rigid motion sequences through low-dimensional spatial representations of images, followed by the incorporation of time encoding and self-attention neural network layers. This approach effectively captures long-term dependencies of fetal brain motion, addresses alignment errors due to contrast changes and severe motion artifacts, and provides geometric deformation estimation to address image distortions among all time frames. The method's significance lies in its ability to learn spatial-temporal representations via deep neural networks for fetal motion tracking without data augmentation, making it a valuable tool for accurately measuring, tracking, and correcting fetal motion in fetal MRI. The research paper discusses the limitations of existing motion estimation techniques in MRI sequences, particularly in capturing large and rapid fetal movements. It highlights advancements made by deep learning approaches, such as predicting 3D rigid transformations and real-time fetal motion tracking using CNNs and transformer-based models. However, these methods still face difficulties in capturing true spatial-temporal relationships due to their fixed image context range and susceptibility to unpredictable motions and distortions. The paper proposes a novel spatial-temporal model capable of considering the entire sequence, mitigating motion correction errors arising from motion artifacts, contrast changes, and image distortions across different time points. The core contributions include a predictive approach in dynamically learning fetal brain movements spatio-temporally through deep equivariant representations without data augmentation. The framework outperforms state-of-the-art methods in motion tracking accuracy while ensuring stable convergence of training and fast inference, holding significant clinical value for real-time motion monitoring tasks. The SpaER framework offers an efficient method for real-time fetal head motion tracking, leveraging a novel approach to rigid motion estimation without requiring network retraining. This approach is grounded in learning spatio-temporal representations through deep neural networks and builds upon recent work utilizing equivariant filters for rigid transformation estimation. The rigid motion estimation process within SpaER involves minimizing the distance between transformed source and target images. This is achieved by utilizing the spatial means of images, calculated through reduced non-negative equivariant filters, to compute the rigid transformation. This framework provides the foundation for efficient fetal motion tracking and perspective steering systems, significantly advancing the field of fetal imaging and monitoring. The authors propose a novel approach to spatio-temporal rigid motion estimation, formulating an optimization objective to find the optimal path of rigid movement. This is achieved by minimizing the distance between the aligned and target image sequences, as expressed in equation 3, where the distance term, dist, measures the dissimilarity between the two sequences and can be instantiated as sum of squared differences, normalized cross-correlation, or mutual information. The authors derive a closed-form solution for both translation and rotation parameters, characterizing the rigid transformation qt between time points t and t+1, as expressed in equation 4. This solution involves the rotation matrix RT, real orthogonal matrices UT and VT, and a diagonal matrix sigma t with non-negative real numbers on the diagonal. The paper then presents a deep learning model specifically designed to estimate rigid motions, comprising 3 submodules: a boosted rigid motion correction neural network parameterized by equivariant filters, a temporal encoding module that incorporates time information into the equivariant features, and a self-attention neural network that learns feature correspondence across different time points. The equivariant neural network, parameterized by theta, captures rotation equivariant representations using 3D steerable CNNs. The spatio-temporal encoding scheme, inspired by previous work, maps time information to image features, outputting ER using a positional embedding matrix, as computed in equation 5. This encoding scheme utilizes sine and cosine functions with a learnable frequency alpha to compute the element on the TTH position of the encoding matrix. The SpaER framework, designed to learn spatio-temporal equivariant representations in latent space, efficiently tracks fetal motion. It encodes input sequences into low-dimensional spatial means, feeding them into an equivariant neural network to extract spatio-temporal equivariant features. These features are combined with temporal features using self-attention layers, resulting in a joint representation that incorporates both spatial and temporal information. The network architecture consists of three main components: input data, networks that encode temporal and spatial features, and the output-aligned sequence with a joint geometric distortion correction module. The self-attention network integrates temporal features with spatial means through elementwise addition, denoted as x circled plus rho, and parameterized as phi. The resulting features, z, are employed to enhance the closed-form solution in equation 4, facilitating the generation of aligned images. The geometric deformation correction module utilizes a net-based predictive deformable image registration neural network to estimate diffeomorphic deformations. The loss function, LGO, is formulated as the sum of a similarity term and a regularization term, where the similarity term measures the distance between the deformed and target images, and the regularization term ensures differentiable, bijective mappings with differentiable inverses. This formulation is based on large deformation diffeomorphic metric mapping, LDDMM, and image registration using stationary velocity fields. The proposed approach addresses local distortions by employing a diffeomorphic deformation estimation model, which guides the motion correction network. The use of diffeomorphic deformations enables the incorporation of both temporal and spatial information, leading to improved performance in fetal motion tracking. Wang et al. Introduce a novel network loss function for training neural networks in fetal MRI scans. This total loss function combines a data term and geometric regularization, with a weighting factor to balance their contributions. The data term measures the difference between the predicted and ground truth images, while the geometric regularization term encourages spatial smoothness and continuity in the motion-corrected images. The authors evaluate their SpaER model against other static learning-based motion correction methods on a dataset of 240 sequences from 15 subjects. The SpaER model is trained using an atom optimizer with cosine annealing for the learning rate schedule, allowing for efficient optimization of the loss function. A detailed analysis of motion correction errors and alignment accuracy reveals the effectiveness and stability of the SpaER model. Specifically, the results in Table 1 show that the SpaER model produces the best motion correction errors among all tested models, outperforming state-of-the-art methods. The SpaER model's superior performance can be attributed to its ability to balance data fidelity and geometric regularization, leading to more accurate motion correction and improved image quality. The author's proposed method has significant implications for fetal MRI scans, where motion artifacts can severely degrade image quality and hinder diagnosis. Comparative analysis of fetal motion tracking methods. Fetal motion tracking is a crucial aspect of fetal MRI scans, as it directly impacts diagnostic accuracy. This study presents a comprehensive evaluation of various fetal motion tracking methods, with a focus on the efficiency and accuracy of the SpaER method. The SpaER method is compared to other prominent methods, including the equivariant filter, Keymorph, and deep pose. Two case studies are presented, featuring visualizations of motion tracking results, with the target fetal brains highlighted using red contours. The results demonstrate that the SpaER method outperforms its counterparts, achieving the lowest errors in motion tracking, with an approximate movement of 3.8 mm for the fetal brain. Moreover, the SpaER method exhibits the lowest variance between adjacent 3D volumes, indicating superior motion tracking accuracy. Visual comparisons further underscore the effectiveness of the SpaER method in accurately tracking fetal brain motion. This is critical for improving the quality of fetal MRI scans and enhancing diagnostic accuracy. The findings suggest that the SpaER method has the potential to significantly enhance fetal MRI technology, ultimately leading to better patient care. The superior performance of the SpaER method is attributed to its ability to accurately capture fetal brain motion, which is essential for producing high-quality MRI scans. The results of this study highlight the importance of accurate motion tracking in fetal MRI and demonstrate the SpaER method's potential to improve diagnostic outcomes. Table 1 presents a comparative analysis of motion correction performance for various methods on 70 real fetal fMRI scans with simulated motions. The proposed method outperforms existing approaches, such as equivariant filter, chemorph, and deep pose, in terms of translation and rotation errors. Notably, the proposed method achieves a translation error of 3.81 plus or minus 1.05 mm and an angular error of 2.76 plus or minus 1.13 degrees, demonstrating superior motion correction capabilities. Figure 3 illustrates the motion tracking performance of the proposed model across varying degrees and lengths of motion sequences. The results show that the model exhibits superior accuracy in handling real motions, ranging from small to large, and maintains comparable motion tracking accuracy when dealing with extended data sequences. This highlights the high stability and robustness of the proposed model in correcting severe fetal brain movements. Additionally, the average time consumption for adjacent pairs and the entire sequence is reported, indicating an efficient computation time of 10 seconds for a 4D sequence. The results of motion tracking for two representative cases are visualized in Figure 2. Showcasing the superior performance of the proposed model in correcting rigid motions and geometric distortions. The model outperforms other baselines by producing the best alignment results with negligible errors. The paper concludes by highlighting the novelty of the proposed model, which learns spatio-temporal equivariant representations for fetal motion tracking. Unlike existing approaches that estimate motion parameters at individual time frames, the proposed approach takes a temporal perspective on the motion pattern of the fetal brain, achieving superior motion correction performance. SpaER, a novel framework for efficient fetal motion tracking, integrates time information into low-dimensional spatial means of image data. This approach excels in achieving the best and most stable performance across unpredictable fetal motions and excessive movement of fetuses, both in simulated and real scenarios. The study showcases great potential in real-time tracking and steering for fetal head monitoring systems. A promising avenue for future research involves applying the trained model to various image modalities for motion correction tasks without requiring network retraining, as it inherently learns the characteristics of rigid transformations. The research was supported by the National Institute of Biomedical Imaging and Bioengineering, the National Institute of Neurological Disorders and Stroke, and Eunice Kennedy Shriver National Institute of Child Health and Human Development of the National Institutes of Health, NIH, under award numbers R01NS 106030, R01EBO 31849, R01EBO 32366, and R01HD 109395. It was also partly supported by NVIDIA Corporation and utilized NVIDIA RTX A6000 and RTX A5000 GPUs. The authors present a comprehensive list of 23 key terms and concepts related to the field of artificial intelligence, emphasizing their significance in contemporary research. This compilation serves as a valuable resource for both novice and experienced researchers, providing a clear understanding of the fundamental principles and their applications. The research in fetal motion tracking has made significant contributions to the field, particularly in the context of MRI imaging. Attention mechanisms, metamorphic image transformation, and deformable geometric shapes are emphasized for robust and adaptable tracking algorithms. Motion correction in MRI and advancements in implicit neural representations for slice-to-volume reconstruction are also highlighted. This overview underscores the need for further innovation in fetal motion tracking.